And we'll now move on to Erald Kolasi, who works at the Urban Institute in Washington, D.C., and he's going to talk about the physics of capitalism. So, Erald, you can take it away.
Okay, thank you, Michael. Can everyone see my screen?
Yes, I can.
Okay, so it looks like we might have a thunderstorm here near DC. So hopefully I don't get hopefully I stay online, basically. Anyway, so thank you, Michael, for hosting this, and thank you to everyone who's in this talk. It's a great honor to speak to you all. So today I'm going to be talking about the ecological crisis and the limits of efficiency strategies. So this, what I'm going to be showing you in this presentation builds off work that I did in 2018 in an article I published in the monthly review called The Physics of Capitalism. So the first thing I want to mention is that when I talk about the ecological crisis, yes, I'm talking about global warming, but I'm talking about so much more than that, right? I'm talking about the nitrogen crisis and the destruction of wild habitats and mass extinctions and all of that stuff. Basically, all of the ecological instabilities associated with the phenomenal growth of human civilization over the last few centuries. Okay, so let's begin with an introduction to sort of motivate the discussion. So human societies, they consume energy from the natural world, right? And then they dump most of the energy that they consume back out into the natural world, right? Now, these energy losses are important because they can power the formation of other dynamical systems, such as storms, viruses, and bacteria. All right, and then these ecological instabilities can then interact with our society again in a kind of chaotic feedback loop, and they can be severely disruptive. And so that's my tongue-in-cheek term here for what's happening, chaos. This just basically means that as society interacts with nature, nature throws a lot of unforeseen consequences our way. Now, you shouldn't read these as Venn diagrams. I obviously realize that society is a part of nature since we're all physical systems. But this is just to sort of highlight the relationship. So the main question that I want to focus on in this presentation is at the bottom of the slide here. Can we address our ecological challenges exclusively through technological innovations that are focused on efficiency gains? Or do we also need to think about other strategies for how our societies function and operate? Now, this talk is happening in a context where, a popular response to global warming and to the ecological crisis that we're facing is to say, we're just going to have a lot of technological innovation and there doesn't need to be any fundamental reorganization of human society. We're just going to get through this basically through technology. And so that's the kind of claim that I want to push back on in this talk. But I also want you to keep at the back of your minds that as I push back on it, I'm not dismissing the importance of technological innovation, right? I'm not dismissing the fundamental importance of efficiency gains and of renewable technologies. I think those things are very important. So let me just state that right off the bat, right, in case anybody's confused. Those things are very important, but I also think the context, the wider social and economic context in which they happen is also important. And this talk is meant to get people to think about that social and economic context in which efficiency gains and technological innovations happen. Okay? So this is a plot here from Gail Tverberg at Our Finite World, and it shows global energy consumption basically over the last 2 centuries. And this is the story of the world economy over the last 200 years, a phenomenal growth in energy consumption. The y-axis is in exajoules, exa meaning 10 to the 18th. And in particular, note obviously the huge rise in energy consumption, but also the phenomenal growth of fossil fuels, right? So coal, oil, natural gas. And keep this in mind because we'll come back to it later in the talk. So when I talk about efficiency, what do I mean? Because efficiency is one of those words that means many different things in many different fields, right? But both in the social sciences, but also in the natural sciences. So here I'm just talking about a simple thermodynamic efficiency. So just the useful energy that you get out from whatever energy you put in. All right, but specifically, I want to focus on aggregate efficiency. So the total amount of useful energy that a society produces in a given year divided by the total energy that it consumed in that year. You can also define this quantity, and people have, as we'll see, for a collection of technological systems if you don't want to define it for an entire society. Okay. So what are the constraints on how efficiency changes? Well, the big ones are, nature, ecology, economics. So obviously nature, through things like the second law of thermodynamics, imposes absolute limits on how efficient our technological systems can be. So, examples would be things like steam engines and internal combustion engines cannot be more efficient than a Carnot engine. So nature herself imposes limits. Another example would be, the amount of transistors you can pack into a computer chip. That's limited by quantum interactions. Quantum limits on Moore's law would be another example. So beyond the limits that nature herself imposes, then there's also limits that, develop as a result of our social and economic structures. And we're going to see concrete examples of that later in the talk. So all of this is to lead up to this question, which is the first major question I want to address as we look at efficiency, is has aggregate efficiency for the global economy changed all that much in the last few centuries? So there have been many people who have taken a look at not exactly this question, but at questions like this. So Benjamin Warr, Robert Ayers, and many of their collaborators, they calculated changes in aggregate efficiency for many different countries and technological systems. So in 2006, for example, they estimated an 8 percentage point rise in the aggregate efficiency of the United States from 1900 to 2000. And if you want those exact numbers, it went from roughly 3% to 11%. So what should we make of this increase? Is this an impressive rise? Is this fast? Is this slow? It's a question that we're interested in, right? Because we all want to make our societies more efficient so that we, in effect, dump less stuff to the environment, right? And so that we have less of these chaotic feedback loops coming from nature. So how should we look at results like this? And I think how you look at them really depends on the context. So if your context is 1900 to 2000, just the 20th century alone, this does look like an impressive result. But if you ask, let's say, how has global aggregate efficiency changed over the last 1,000 years? There, I think the answer is fundamentally more ambiguous, because for most of that time, the systems that were doing the work that powered our civilizations were things like human and animal muscles, watermills, windmills. And those things, we know from a lot of research that has been done, typically have efficiencies on the order of 20 to 30%, right? Modern, watermills and windmills, they might have much higher efficiencies than that, obviously, but I'm talking about the ones that might have been used, let's say, centuries ago. So I would argue that if you actually look at the aggregate efficiency of the global economy over long stretches of time, what you see with the rise of capitalism is a huge dip in aggregate efficiency. And then you get to a point like 1900 where the aggregate efficiency is so low, there's basically nowhere to go but up, right? And so that's why a result like this might look impressive. So that is one major claim that I'm making here, is that aggregate efficiencies, change at very slow rates, and that the transition to capitalism was accompanied by a decline in aggregate efficiency, and now we're sort of clawing our way back up to what we were for most of human history. Okay, so that is, and we're going to understand why this happens through an example that I'm going to bring up shortly. Another major factor when we talk about efficiency is what economists call the rebound effect, right? So the rebound effect is the idea that if you have a rise in efficiency, the energy savings that you get are less than what you would expect. So this is kind of a toy example that I'm showing in this slide. So let's say you bought a really fuel efficient car, and you notice, oh, you know, gas costs less. So now you have more money, right? You have more money to spend on something else, and you say, well, let me take a holiday in Spain. Now that's obviously an extreme example, but you can imagine how this works when you're saving a bunch of money from many other systems. You might shift your spending activities towards something else, and of course that something else will require energy. And so that's the idea of the rebound effect, that you know, when you have this increase in fuel efficiency, you're not going to get an exact corresponding decrease in fuel consumption. So if you had a 5% rise in fuel efficiency, you won't necessarily get a 5% drop in fuel consumption. Economists and other researchers, they've looked at sort of two different quantities when it comes to rebound effects, and that's microeconomic rebound effects and macroeconomic rebound effects. So microeconomic rebound effects would be things like, you know, if a household, you know, replaces its lights with like LEDs or something, you know, how much does their electricity usage drop? Macroeconomic rebounds would be things like if the government of a particular society enacts a certain policy designed to save energy, or designed to increase efficiency, what are the consequences for energy usage? So for this talk, I'm mostly interested in the macro numbers. And those have been typically estimated to be around 50 to 60%. So what that means basically is that as societies become more efficient, it is true that they use less energy over the timescales that have been studied. But the drops are not as, the drops in energy usage are not as much as you might expect, right? I mean, 50 to 60% macroeconomic rebounds are still pretty significant. And you know, this is an important point, because if we only have this limited amount of time, we only have basically this century to truly tackle our massive ecological challenges, we seriously need to think about whether, you know, pursuing efficiency gains at the exclusion of anything else is a good idea when these rebound effects are fairly large, right? When we're not getting the drops in energy use and consumption that we would need. So that's another thing to keep in the back of your head there. So let me look now at a particular example. Right now, the discussion has sort of been very broad, presented work that some other people have done, and now I'm gonna look at a concrete example, and we're gonna look at steam engine in Britain in the 18th century. So I just want you to focus on the Newcomen and the Watt engine here, and don't worry so much about the Poppin engine. So in the 17th century, Britain had this massive shift towards coal use. And as people started digging underground into coal mines, a major problem became water would end up flooding the mines. So this would be water in underground reservoirs. It could be from rivers or streams or something else, but this became a huge problem. And so there arose this need to somehow remove this water, and typically the way it was done is just like horses would basically like carry the water buckets out. But eventually in the early 18th century, Thomas Newcomen came along, and he designed the first practical steam engine that many coal companies adopted in order to raise this water out of their coal mine so their workers could get back to work. So let's look at how the Newcomen engine worked here. So basically at the bottom here is coal, and you burn the coal, okay, that heats up the water, and then that produces hot steam here in the boiler. Then there's a valve between the boiler and the cylinder, so the hot steam is released to the cylinder, and it pushes the piston. So as the hot steam enters, it pushes the piston. The piston is then attached to a rod here, and then this rod is attached to a rotating beam. Okay, and then basically the beam goes up and down as the piston goes up and down, and it lifts, you know, water buckets or whatever it's attached to. Okay, so so in the first step, the hot steam goes through. Oops, sorry about that. In the first step, the hot steam goes through, pushes the piston up. Okay, then there's this pipe which releases a spray of cold water. Okay, now as the water cools down the temperature inside the cylinder, there's condensation that happens. So there's a lot of the gas particles become liquid water droplets, and the liquid gas mixture occupies. Sorry, my mouse wasn't working there. The liquid gas mixture occupies less volume and exerts less pressure on the cylinder walls. Okay, so in effect, there's a partial pressure that develops inside the cylinder. All right, so sorry, a partial vacuum, not a partial pressure, a partial vacuum. What that means is that the pressure inside the cylinder is less than the atmospheric pressure outside. And because the atmospheric pressure outside is larger, there's a net force on this piston that pushes it back down. And then the process repeats, right? A hot steam goes through again, piston goes up, partial pressure, you know, water spray cools it down, and so on. Now, the problem, one problem with this engine is that the inside of the cylinder is going back and forth between being hot and cold. So it's going back and forth between being hot and cold, and that wastes a lot of energy. Ideally, what you want is you want the inside of the cylinder to be warm, because then it requires less heat energy in the next cycle to push up the piston. So this is what James Watt figured out later in the 18th century by adding this a separate condensation chamber to the cylinder. So in the Watt engine, as the piston comes back down, the hot steam enters the condensation chamber, which is kept permanently cool. Okay, and then again, that results in a partial vacuum as the steam becomes liquid water, and then it becomes liquid. Sorry, my thing's not working here. Yeah. So basically, the inside of the cylinder here is warm, right? The inside of the cylinder is warm. And what that means is that in any given cycle, it requires less heat energy to push up the piston. So that's why Watt's engine effectively doubled the efficiency from the Newcomen engine. So it was a huge result. It was a huge result for Watt, and who would go on to make many other marvelous innovations to the steam engine. But there's a critical but. So Watt and his partner, Matthew Boulton, they received patents for their inventions, and they defended these patents very aggressively in court. It was kind of a dog-eat-dog world back then. They even spied on their competitors. And as a result, the Watt and Boulton engines were quite expensive. And so many coal companies simply opted to buy the cheaper Newcomen engines. And so what happens from about 1770 to 1800 is you have almost 1,000 Newcomen engines that are produced compared to just about 450 Watt and Boulton engines. All right. And then Sabre here, that's another model by Thomas Sabre, who was another inventor earlier in the 18th century. So what we see is that, yes, Watt's engine was much more efficient, but it did not diffuse as rapidly, certainly not as rapidly as historians thought earlier in the 20th century. More work has now revealed that the Newcomen engine remained fairly dominant throughout most of the 18th century. In fact, there were Newcomen engines being used up until the middle of the 19th century. Now, another critical point to emphasize here is that there were roughly 15,000 watermills in the 18th century Britain, about 10 to 20,000, not taking the average there. And in many critical industries like textiles, these perform the vast majority of the mechanical work. So that's also key as you try to understand here how these aggregate efficiencies are evolving. So if you look at the bottom here, this bottom plot, okay, that's the aggregate efficiency of steam engines in 18th century Britain. And the top plot is the aggregate efficiency of the engines and the watermills. okay? So you can see a gradual improvement in aggregate efficiency, okay, as you go across the 18th century, and obviously it accelerates here as Watt's inventions come online. But on the other end of the spectrum, once you include the Watermills, you can see that the results look quite different. Its aggregate efficiency is actually declining because the Watermills just started off being more efficient. And I'm conservatively estimating 15% here. They're probably higher than that. But as the steam engines come online, there's this decrease. This sharp decrease here is due to some improvements that Smeaton made to the Newcomen engines, as well as to more Newcomen engines being produced towards the end of the 18th century, and then more Watt engines as well. So that's why it's weighted more heavily by their number there. Now, when it comes to the top lot, the steam engines and the Watermills, I am differentiating here in their power output. So for the steam engines, their power output was roughly the same for the first decade after Watt's engines became available. And then Watt's engines had a higher power output. But I'm assuming they have the same power output. However, there is a big difference between the power output of the Watermills and the engines. And so that will affect the aggregate efficiency. Another thing that's important for aggregate efficiency is the time of operation. So if more inefficient systems are operating for a longer time, they'll skew the aggregate efficiency that way. For the purposes of this plot, just because it's impossible to get that historical data, I'm just assuming that that they're all operating for the same time in any given year, basically. All the steam engines and all the Watermills. I know that's an incorrect assumption. The Watermills are probably operating for longer periods of time than the steam engines, because the steam engines, they break down, they have technical issues and stuff like that, they have to be repaired. So, but anyway, I'm assuming they operate for the same time in any given year. So now I want to bring this discussion forward, much more forward, to renewables. Yeah.
Erald, you have about 5 minutes left for Q&A.
Sounds good.
So would you like to take that, or you want to continue?
I'm almost done. I just have a couple more slides.
Okay.
So these numbers that I'm showing here are from BP's review of statistical review of world energy. And you can see that fossil fuels still account for 85% of global energy consumption, despite the fact that renewables have made vast strides over the last 2 decades in many different areas, or cost and efficiency and all these things. That have mainly Western countries, but in some other areas as well, they've been offset by fossil fuel gains in other parts of the world. So I have some food for thought here. These are some examples that maybe we can consider in Q&A, but I especially want to focus on Germany, because Germany gets a lot of press. Germany looks like it's going to meet its carbon emissions target for 2020, and that was a 40% reduction relative to 1990. I think as of 2019, they were at about 36% reduction is where they'd gotten to. So, and people thought that last year they would fail to meet it, but now because of the coronavirus pandemic and much of the German economy shutting down, it looks like they will succeed in actually meeting that. Germany, one of these societies that has made many major strides in renewables. So renewable energy accounts for about half of all electricity generation in Germany, which is an amazing fact considering that Germany is a pretty large country. However, there are important, social and political circumstances about Germany that may not apply as easily to the rest of the world. So, a huge part of that drop in emissions in Germany can be attributed to the collapse of the heavy industries from East Germany. So after East Germany collapses in 1990, you have the heavy industries there lose the political backing of the communist government, and so many of them go under. That explained about 50% of the carbon emissions drop that happened in the 1990s in Germany. A large part of the explanation can also be attributed to the fact that after the fall of the communist regimes in Eastern Europe, there's a lot of German industries that shift their manufacturing to the east. Again, that has an effect of lowering carbon emissions in Germany. But the point is that a lot of those emissions didn't happen because of government policy or because of market solutions and related to technological innovations. They happen because of these profound historical political shifts, which are difficult to duplicate. And so it's just something to keep in mind. And we can talk about China and Tesla later in Q&A if somebody wants to ask about them. But I'll just go back to my conclusion, which is, so just three main points here. Financial incentives and social institutions impose very powerful constraints on the diffusion and distribution of technological systems. Aggregate efficiencies for entire economies change at very slow rates. And that, I think, means we need a broader strategy in how we respond to our ecological crisis, such as stabilizing consumption and other direct forms of state intervention. And finally, I do think it's important to pursue efficiency gains. I want to see a lot more public investments in that area in particular, but I think it should be done in the context of stabilizing energy consumption, right? We also need to think about how to create social and economic structures that are less disruptive to our ecosphere instead of just having more technological innovation. So thank you. And if you have questions, if you want my data, if you want my Excel files or anything like that, you can email me at erald.kolasi@gmail.com. And I'll take questions.
Okay, Erald, thank you very much. We have 17 participants here. Would anybody?
Could I ask a question?
Yes, please.
So these efficiency measurements, do they include only the energy input and energy output ratios, or do they also include the energy that might go into the newly designed plant and systems, and employment and human manpower that goes into the new systems that change the energy efficiency? The definition of energy efficiency, is it only at the point of the plant itself, or does it include the manufacture of the plant, energy that goes into manufacturing and operation of the plant that creates those additional efficiencies?
Okay, we only have time for a quick response.
Yeah, so to answer your question, no, it generally does not include those things. It's meant to be kind of, exergy is another term, so the amount of available energy that actually gets converted into useful work. But it doesn't, but there are many other ways to think about efficiency that this measure doesn't include.
So I asked because at the aggregate level, all those other energy costs will also matter for society.
Yeah, of course. So this is not an absolute, obviously, aggregate calculation. This was an aggregate calculation for a certain kind of efficiency for certain technological systems. I think to calculate an aggregate efficiency, which includes all those things for all of society, as you understand, is quite challenging, and the data is highly uncertain. And so, but good question.
I'm not actually certain. Is there a panel immediately following us, or is there some kind of break right now? I should know that, but we're not getting any people requesting.
I think there's a panel at 1:30 or 4:30 East Coast time.
Okay, so we actually, it's 4:15. We don't have to be super rigid with calling this to an end if there happen to be a few more questions.
There's a keynote in plenary after this. There's a bit of a quote-unquote networking break, but depending on how much you can network in a pandemic.
That's immediately following this?
Yeah, at 4:30.
Yeah.
4:30. Well, okay. And we still have a little time here. Would anybody else like to?
I'll ask a question. So,
please.
I wasn't quite sure, Erald, I came in a couple minutes late. You were noting the lack of shift to the Watt engine, despite it was more efficient, or a slow transition to it, and then talking about the rebound effect. I'm not exactly sure what you were saying there, that it might take longer to do something, have the rebound effect occur than we might think, or.
I think those were kind of two separate points. The point of the Watt engine was to show that aggregate efficiencies over long time scales kind of change at very slow rates. And that has to do with, in certain cases, not always, with how society and with how society is organized, right? So a big reason why the Watt engine did not diffuse as rapidly as initially believed is because a lot of these economic and political constraints. And so a lot of coal companies just did not want the huge upfront costs of buying a Watt engine. So they went into the Newcomen engines for a while. Now, what happens later in the 19th century is that it's not even about the Watt engine. Then the high pressure steam engine comes along, right? Richard Trevithick and the designs that he makes, and then later generations of high pressure steam engines. And those take over, and those are the ones that end up going with steamboats in the Mississippi and the trains. And so those do have much higher efficiencies, but Watt himself was very scared about using high pressure steam engines. Launched a propaganda campaign against them in the early 19th century when one of them blew up, one of Trevithick's designs. So yeah, it's the social dynamics behind how technology spreads are very fascinating. And that's kind of what I was emphasizing in that point. The rebound effect was a separate point.
But what about just the pure physical thing? I think Bejan in his keynote today was saying evolution doesn't throw things away. Effectively here, people would be saying, well, I'm not going to throw away my Newcomen engine just to use a Watt engine. And yeah, if I didn't have one already, maybe I'd buy one, but I already have a Newcomen and I don't have the money, so I'm not going to throw it away, and it'll just take me time to get the new model. Yeah,
I think, I think there's something to that. I think talking about evolution, I think even the evolution of the design, you can talk about that, because Watt, when he made his improvements, he was experimenting on Watt's engines. On Newcomen's engines. So yeah.
Phil Metz, did you have a question?
I had a question. Erald, are you familiar with the work of Skip Leitner?
I'm sorry, Phil. Say that name again.
Are you familiar with Skip Leitner? Laitner. He's done some really good on aggregate energy efficiency, particularly of the U.S., but other places as well.
Okay. Can I write that name down? Can you spell his last name for me?
Yeah, I can put it in chat too, but it's Laitner.
Okay, and then Skip was his first name.
He goes by Skip. I think it's actually John or something like that. But if you just look up Skip Leitner, you'll find it, and you can contact me if you want. He's written some really excellent papers on trends in energy efficiency of society over, last century or so.
Okay. Yeah, absolutely. I'll look into that.
I have a question.
Please.
Yes, your rebound at the beginning of your presentation sounds a lot like the Jevons paradox. I'm familiar with that.
I'm very familiar with that. And notice how I didn't mention anything about it. So there's a general consensus now that the Jevons paradox does not happen, again, for at the economy-wide scale. But there's also, I mentioned in the slide, there are huge uncertainties about these things, right? Because it depends on which economic models you want to adopt. It depends on the timescales that you look at. And so I personally tend to think that efficiency gains for at the level of entire economies are still a good thing to have. They still lead to less energy usage. Yeah. But again, how much less energy usage, that's a black box.
Okay, thank you.
Yeah, Errol, I'll just say that amongst my group, I don't think I confirm that there's a consensus. This particular conference might not agree with your statement of consensus, which I think is present in the orthodox economics.
Yeah, so let me, and that's a great point. Yes, when I say consensus, I mean amongst sort of neoclassical economists or some other people who have looked at this. Ecological economists, they may recognize the presence of a Jevons paradox. The Jevons paradox being that when you have increased fuel efficiency, you end up using more energy because of the increase in fuel efficiency, not less. So just to clarify that for others.
Right. What's the difference between that and rebound effect? I actually always thought they were the same thing.
I'm sorry, what was the question?
What is the difference between Jevons paradox and rebound effect? I actually thought they were the same.
So here's an explanation of the difference through a simple example. Let's say you have a 5% rise in fuel efficiency, okay? For there to be a Jevons paradox, it would be if you had like a 2% gain in energy usage as a result of that, okay? Whereas if you had a 5% rise in fuel efficiency, but only, let's say, a 3% drop in energy consumption, that's a rebound effect, right? In that case, the rebound is what, 40%.
Okay.
So in other words, for the rebound effect, you have less energy use as a result of higher efficiency, but just not as much as you expected. Whereas for the Jevons paradox, you actually have more energy usage as a result of your fuel efficiency. That economists sometimes call that backfire, or the BK postulate, if these names ring a bell.
Right.
I think that was an accurate summary of the terms. If you haven't read, and perhaps you have, stuff on what people would call useful work or useful exergy, which is essentially energy consumption times efficiency of conversion to what we would call mechanical work. That's roughly proportional to, or from the countries analyzed, seems proportional to GDP, which suggests the economy is just a heat engine, a large heat engine, so that you can gain GDP either by energy increases or efficiency increases, or one or the other, or both. That's along the lines of stuff you're investigating, so I'm just suggesting that to you.
Yeah, absolutely. I'll definitely.
Any other questions here? Okay, why don't we, if no one else has a question, we'll call it a day. And Erald, thank you very much.
Yeah, thank you so much.
Mm-hmm.